In previous lectures, we have already learned what are the double integrals and what are the triple integrals. We also noted that surface and volume integrals are represented by double and triple integrals. In this lecture, we will learn the surface integral and find the mass of a plane lamina, means plane body. So let us start with an example. The first example that we are taking is evaluate the integral, double integral xy dx dy over the region bounded by the line x plus y is equal to 1 and the coordinate axis. The very first thing that we should do is that we should draw the region. So let these are the x and y axes. So how does you draw this line? When x is 0, y is 1, and y is 0, x is 1. Means take this point as 1 comma 0 and this point as 0 comma 1. This point is 0 comma 1. So the straight line joining these points is x plus y is equal to 1, and this is x-axis, this is y-axis, this is x-axis. So this is the region bounded by these three lines, means axis and the specific line. So we have to integrate xy over this region, and this region is a triangular region. So let us start this let us start to evaluate this integral solution. Let I is equal to double integral over the region xy dx dy, where r is this region. This region is denoted as r. So now you can see that limits of x and y are very easy to put. We have already seen the same thing in the previous lecture, but I am again elaborating the thing. The value of x means limit of x will be, this is origin, so this is 0 0. So limit of x is 0 to 1, and limit of y is 0 to 1 minus xy. In the previous lecture, we elaborated that first we put minimum to maximum value of the region for x. So for this bounded region, minimum value of x is 0 and maximum value of x is 1. So x varies from 0 to 1. And again, while defining the double integral, we learned that the value of y is taken from the lower and upper curve. So lower curve of the region is this line x-axis. So here y is 0, and at every point, means for each value of x, the upper curve is given by this line x plus y is equal to 1. So value of y is 1 minus x at each point on this line. So lower limit of x is 0 on x-axis, and upper limit of y is on this line, means 1 minus x. So y is equal to 1 minus x. So put these limits, and now I become 0 to 1, 0 to 1 minus x, xy dx dy. We have already learned in the previous lecture how to integrate this. So this is variable limit 1 minus x for y. So y will, integration with respect to y will be performed first. So this is 0 to 1 x, y integrated gives y square by 2, and the limit is 0 to 1 minus x dx. Then now it is very easy. So 1 by 2, 0 to 1 x into 1 minus x whole square dx, and you can evaluate this. This comes out to be 1 by 24. You can easily evaluate this. Just open 1 minus x square as 1 minus 2x plus x square and multiply with this x. So you will integrate, and we'll get this value. So this integral evaluates to 1 by 24. For the sake of completion, I am completing the same thing here. X into 1 minus x whole square. This means x 1 minus 2x plus x square, and this means x minus 2x square plus x cube, and you can see this will integrate to x square, this 2x square x cube by 3, and this to x to the power 4 by 4. So you will get what? You will get x square by 2 minus 2 x cube by 3 plus x to the power 4 by 4, and you will put the limit 0 to 1. So this is 1 by 2 minus 2 by 3 plus 1 by 4, and this is equal to 1 by 24. So this is how you integrate. So I have completed the whole task, whole integral, and the answer is 1 by 24. We take the next example. An ax of uniform thickness is of the shape bounded by the lines x is equal to 0, x is equal to 1, y is equal to 0, and the curve y square is equal to x square plus 1 in first quadrant. If the density of the x is given by rho is equal to 1 by x square plus y square, find the mass of the x. So the first thing is that we should draw the figure. We should draw the shape of the x. So let this be y-axis and this be x-axis. This is y-axis, this is x-axis. Now what are the lines? X is equal to 0. This y-axis is x is equal to 0. Y is equal to 0. X-axis is y is equal to 0. And for x is equal to 1, take a point 1 comma 0 at x-axis, and a vertical line at this point will be x is equal to 1. So we have drawn three lines. Now we have to see the shape of this curve. So this y square is equal to x square plus 1 means y is equal to plus minus square root of x square plus 1. So y is equal to, because the shape is symmetric about y-axis as well as x-axis, so if we draw this curve, when x is equal to 0, y is equal to plus minus 1, plus 1 minus 1. When y is equal to 0, x has no real values. So this will not pass through origin. So the curve is actually a hyperbola of this type. This, so this is lower branch y is equal to square root of x square plus 1 minus times, and this is upper branch y is equal to plus times square root of x square plus 1. Because the question says the shape lies in first quadrant, so we will ignore this lower part and we will consider only the upper part. So let us erase all these things and draw this shape in the uh, coordinate axis that we have drawn for the x. So what is that? This shape. Suppose this is y is equal to 1, so this will like something like this, and the equation of this curve is y is equal to square root of x square plus 1. So this is our shape of the x, and we have to find the density of the same thing. So what is the density? You know that density is given by, sorry, mass, we have to find the mass. So you know that mass is given by density into volume. But the question says that lamina means axis of uniform thickness, and due to uniform thickness and density does not contain the term in variable z, so the density is per unit area. So this rho is per unit area. In this sense, our become mass will become density into area. So what is our area? Let us start with taking an elementary area. So let this be an elementary area of thickness dx and of sides dx and dy. So area of this element is dx dy. So mass of element dx dy is equal to rho dx dy. What is rho? Rho is density, and what is dx dy? Dx dy is area. So density into area. So this is mass of this element. What now remains is that integrate this mass over the whole area. So mass of the x, let it be noted as m. So this is double integral over the region of x rho dx dy. This is our total mass. Now we should put the limits. So m is equal to this. Rho is 1 by 1 plus x square plus y square dx dy. And now we should put the limits. So we already have discussed that limit of x is taken from minimum to maximum. So x limit is varies from 0 to 1. And what is the limit of y? For limit of y, we take a strip of this type, and limit is decided from lower and upper curve. So at the lower curve means x-axis, everywhere y is 0. So lower limit of y is 0, and at the upper curve at each point y is square root of x square plus 1. So this upper limit is square root of x square plus 1. Now we have reached with an integral of the form I is equal to, or simply we have said it m. So m is equal to 0 to 1, 0 to square root of x square plus 1, 1 by 1 plus x square plus y square dx dy. Now we will integrate with respect to y first. We have already discussed a lot about this. So let I is equal to 0 to square root of x square plus 1 by 1 plus x square plus y square dy, and because x is constant here, so we can take x square plus 1. Let us take x square plus 1 is equal to alpha square, and that will give us 0 to alpha 1 by alpha square plus y square. Because the integral is complicated, so we are breaking it first, integrating the inner one, then we will put I into the integral to integrate outer one. So this dy, and this is simple integral, so this will be 1 by alpha tan inverse y by alpha, and limits vary from 0 to alpha. So when you put y is equal to alpha, tan inverse x, tan inverse 1, this is pi by 4, and when you put alpha y is equal to 0, so this is 0. So we obtained pi by 4, 1 by alpha, and alpha is x square plus 1. So we got pi by 4, 1 by square root of x square plus 1. This is our value of I, means the inner integral. We have now integrated the inner part and put the value of I here. So we are getting m is equal to pi by 4, 0 to 1 dxy square root of x square plus 1. So I hope you know this integral. This is standard integral, and value is cos uh, hyper sine hyperbolic inverse, sine hyperbolic inverse sine hyperbolic inverse x, and the limit is 0 to 1. So this is pi by 4 sine hyperbolic inverse 1, and at x is equal to 0 sine hyperbolic is 0. So this is the mass of our x. So finally mass of x is equal to pi by 4 sine hyperbolic inverse 1. You can also integrate this in logarithm. So if you want to integrate this in logarithm, this yields to 1 by square root of x square plus 1 dx. This is equal to x plus square root of x square plus 1, and then if you put the limits 0 to 1, at the lower limit log 1 is 0, and at the upper limit this is log 1 plus root 2. So in that sense mass will become pi by 4 log of 1 plus root 2. So this is how we find the mass of a plane lamina. And let us take one more question. Let us take our next example. So we take this example, evaluate the double integral xy dx dy over the region bounded by the axis line x is equal to 2a and the curve x square is equal to 4ay, a greater than 0, a is positive. Again we start by drawing the axis and the shape. So let this be x-axis and this be our y-axis. So these are axes. Another line is x is equal to 2a. So let this be a point A on x-axis, this be a point 2a on the x-axis. So a vertical line drawn at x is equal to 2a. This is line x is equal to 2a. Now we have to draw this curve. This curve you can see, this is parabola y is equal to 1 by 4ax square. So this will draw something like this, and this is y is equal to 1 by 4a x square. This is our curve. So this is the region bounded by these lines and curve. So we have to evaluate this integral over this region. So let us start evaluation. Let I is equal to double integral over the region xy dx dy. What is this r? R is this region. This region is called r. This is the r region. So now we have to put the limits. Put the limit. What are the limits? So you can see this question is simpler. Lower limit x has the limit 0 to 2a. So 0 to 2a. We have already discussed that x takes the minimum to maximum value, and then limit of y. So again I should remind you that take a strip, and limit of y is taken from the curve, lower limit from this lower curve, so y is equal to 0, and upper limit from upper curve, so y is equal to 1 by 4a x square, and then xy dx dy. Again y has variable limits, so we will integrate with respect to y first. So this is 0 to 2a, and then integrate y, it will become 1 by 2y square, and the limits are 0 to 1 by 4a x square dx. Now put this limit, so you get 0 to 2a, 1 by 2, lower limit is 0 and upper limit is 1 by 4ax square. So 1 by 4ax square whole square dx, and this simplifies to 1 by 32, 1 by 32 a square, and the limit 0 to 2a x to the power 4 dx, and now you can integrate this very easily. So this is 1 by 32 a square, and x to the power 5 by 5, so 2a to the power 5 by 5. and sorry, there is a mistake. X is there, so the value this takes x also, so this will become x into this means x to the power 5. So x to the power 5 will integrate to 2a to the power 6 by 6. So now 2 to the power 6, you can simplify this. 2 to the power 6 is 64 and by 32, and this is 6, so it be numbers will cancel it out, and finally we will get 1 by 3 a to the power 4, because a square will also cancel a to the power 6. So this is our integral. So let us take our next example. Find the area bounded by the parabolas y square is equal to 4x and x square is equal to 4ay. The very first thing that you should do here is find the point of intersection. So you can easily find points of intersection. Y to the power 4 is equal to 16a square x square, and then 16a square x square is again 4ay. So this is equal to actually 4 cube a cube y, and by taking the both sides on the one side, so we will get y cube minus 4 cube a cube, this is equal to 0. So this will give you y is equal to 0 comma 4a, and you can notice that when y is equal to 0, x is also 0. When y is equal to 4a, x is also 4a. So the points of intersection, the points of intersection of parabolas are 0 0 and 4a 4a. So because these are parabola, you can easily draw. Suppose this is x-axis and this is y-axis, so this will draw something like, look something like this and this. So again mark that y square is equal to 4x should be symmetric about x-axis. So this is y square is equal to 4x, and this is x square is equal to 4ay. So these are the curves, and this is the area bounded between the curve which we need to find out. So area we have discussed in the previous lecture that area is double integral over the region and dy dx. So let us just put the limit. What are the limit? So you can see that this point is 0 0, this point is 4a 4a, means the point corresponding on x-axis, this is 4a comma 0. So just put the value of x, means limit of x from 0 to 4a. We have discussed so much for this. So 0 to 4a, and then for value of y, take a strip, and lower curve will give lower limit, upper curve will give upper limit. So from this point you will get the lower value of y is equal to x square by 4a, and from this point upper limit of y will be received, so this is 2 root ax. This is the limits, and dy dx. So variable limit of y, we have variable limit of y, so integrate y first, you will get 0 to 4a, and then dy will integrate to y, so y, and the limits are x square by 4a, then 2 root ax and dx. So just put 0 to 4a and 2 root ax minus x square by 4a. And I hope that you can now integrate this. This is a pretty easy integral. The final answer after integration, this is x to the power 1 by 2, so you can integrate, and this is x square, so you can integrate. So after integrating and putting the limit, the answer is 16 by 3 a square. So this is our required area. Let us take a final example. Find the area bounded by the curves y square is equal to 2 into 2 minus x and y is equal to 2 minus x. So you can observe that the very first thing that we should find is the point of intersection of these curves. So the most common way is that replace y with x. So we have y square is equal to 2 into 2 minus x. You can directly watch or you can watch by replacing. You can find by replacing. So this will give y square is equal to 2 minus x whole square. This is equal to 2 into 2 minus x, taking all at one side, 2 minus x, then 2 minus x minus 2. So this gives you x is equal to 0 comma 2, means these two curves intersect at 0 comma 2. Again it is worth to notice that when x is 0, y is 2, and when x is 2, y is 0. So from these information you can draw the region bounded by these curves. Suppose this is x-axis, this is y-axis, and x is equal to 0, y is equal to 2. Take this one and 2. So this is point 0 comma 2. This point is 0 comma 2, and when x is equal to 2, y is 0. So 1 and 2, this point is 2 comma 0, here y is 0. So first thing, and both the two curves intersect at these points, means both curves pass at these points. So this is the line. Y is equal to 2 minus x is nothing but x plus y is equal to 2. This is x plus y is equal to 2. This is the line y is equal to 2 minus x, and this is inverse parabola, so this will come like this. This is, so let me change the color so that you are not getting confused. So this is x plus y is equal to 2, and this is y square is equal to 2 minus x. So red curve I have written in red, and purple line I have written in purple. So this is our region bounded by these two curves. So just put the area integral. What is the area integral? Area, we have already discussed a lot about this. So this is double integral dy dx, and now just put the limit. So what are the limits? X takes the limit, this is 0 0 origin, so x take the limit 0 to 2, lower limit minimum value of x is 0 and maximum value is 2, so this is 0 to 2, and y takes the limit. So again draw a strip, and I am reminding you in each question that y takes lower limit from lower curve, upper limit from upper curve. So at lower curve y is 2 minus x, so this is 2 minus x, and at the upper curve y is square root of 2 2 minus x. This is y. So just integrate this. So we will get 0 to 2, and y, limit of y are 2 minus x is square root of 2 2 minus x, then dx, and we get 0 to 2 is square root 2 into square root of 2 minus x minus 2 minus x. This is our standard integral in x. You can very easily integrate this. So this will be square root of 2, 0 to 2 is square root of 2 minus x dx, and minus 0 to 2, 2 minus x dx. So you can see that this integrates to 2 minus x to the power 3 by 2 divided by minus 3 by 2, and this integrates to 2x minus x square by 2, and the limits are 0 to 2. 0 to 2. When you put upper limit, this will become 0 and this also will become 0. So at lower limit you will this second curve, this when you put upper limit, this 4 minus 4 by 2, this will not become 0, this will become 0 at lower limit, and this will become 0 at upper limit. So just put the limits and the answer that you will get is 2 by 3. So this is how we find areas of some surfaces. We also find some mass of laminas, and we will continue to find such things in next lecture. We will continue the series, and in the next lecture, multiple integrals part 4, we will evaluate the volume integrals. So stay connected, and this is not the last. After the volume integral, we will again evaluate surface integral by substitution method in polar coordinate, and then we will evaluate volume integrals in spherical polar coordinate, and in this way we will finally conclude the uh, final content of the multiple integrals. So stay connected and keep on watching the further videos.